sine square t. Then cosine t times 0 will disappear. 0 times cosine t will disappear. And as you can see, this is the value which is negative of a sine square. I will do the integration from 0 to 2 pi of negative sine square t dt. Of course, the integration here, if you remember how to integrate sine square, it's very, very simple. I will need to replace this is sine square t by 1 minus cosine 2t divided by 2, I believe. And then I will be able to evaluate the integration. It's going to be t, this is going to be a sine. Once you make new substitution, you will be able to cure this guy. So just remember the relation that I told you about, which connects sine square and the sine and the cosine of 2t. You will be able to integrate this guy. The result will be, as you can see, will be negative over 1. Now, also I need to use Stokes theory in order for the f of x, y, and z, which is xz, yz, x squared plus y squared, and the z is root of x squared plus y squared, which is actually a hyperparaboloid of one sheet. If I, no, it's going to be a column, so z squared minus x squared plus y squared equal to 0, and the x squared plus y squared less than or equal to 1, oriented upward. So it's a surface inside a cone. Once more, that's the f function. As I told you, the surface is a cone, z equal x squared plus y squared, and inside x squared plus y squared equal to 1, which means, and it is moving upward. Also, this is the surface integration. I will change it to be an integration on the contour. I will need to get dr. So parameterizing the relation, the boundary of the hemisphere circle, which is the intersection between the cone and the cylinder that I have. So once more, x is going to be cosine t, y sine t, and z equal to 1. This is the intersection between them, because this is x squared plus y squared less than or equal to 1. So the cylinder inside the cone will be intersecting at z equal to 1, as you can see. So now r of t is cosine t sine t once more, plus, and this is the z component. So r dash is going to be negative sine of t, cosine t at 0. And in a similar manner, I will take these components, I will start substituting in the f function. Here we go, these are x, y, and t. Making the substitution in f, we ended up having cosine t, sine t, and 1. Make with the substitutions, very, very simple. As you can see, I can replace x by cosine t, and the z is equal to 1. So all you have is cosine t, as you can see, and it will go for the rest of the parts. Multiplying f dot r dash will develop cosine t negative sine t plus sine t times cosine t, which is going to be 0. 1 times 0 is going to be 0, so the integrand is equal to 0. So this guy is equal to 0, so the circular integration will be 0. And that's the value of the vector field integration around this surface. Same way, like you have another problem which expresses paraboloid, as you can see, with an above the disk x squared plus y squared less than or equal to 4, which is 3 dimensions, is a cylinder also. So it's a paraboloid cap, as you can see. So this is the z equation. Inside this x squared y squared less than or equal to 4, which means z equal to 4. Okay, so actually this is the root, this is the surface, I'm sorry, that's the integration through the surface. That's going to be the integration, the corresponding integration on the contour. So getting the r, which is very, very simple, is going to be 2 cosine t, 2 sine t. The 2 here stand for the r, which is 4, so its square root is going to be, that's the parameterization. And of course, z is equal to 0 if you make the substitution. Replacing x squared minus y squared by 4, you will have z equal to 0. Differentiating, so it's going to be negative 2 sine t, 2 cosine t, that's the r dash. taking these components and also making a substitution, and f just by chance it happened that once you make this substitution, the integrants equal to 0, and once more your integration will be 0 around the closed boundary. These 4 examples actually make you capable of understanding the idea of Stokes theory. That's the evaluation of a surface integration through a contour. To the final thing in our course, which is the divergence or Gauss divergence theory, which allows us in evaluating the surface integration, but using triple integration. Let's see. Let J be a simple solid whose boundary sigma is a closed surface, has to be a closed surface, oriented with the exterior normal. If the vector field is given by the components F1, F2, and F3, is a vector field of class C1, so it's differentiable once in order to apply the gradient. On an open set containing G and Fn is the unit vector exterior to the normal vector. So if you are evaluating F dot n, which is the flow of the vector field with the surface as we defined previously, it's going to be simply the triple integration for the divergence of F. So instead of going to the surface integration, we can replace it by the divergence of the vector field, but in triple integration phenomenon. So mainly, Stokes will help you out instead of doing the surface integration into the contour integration. Instead of doing the surface, that's Stokes. In surface integration, going up to triple integration, that's divergent theory 4. Of course, divergence, as we defined previously, is the derivative of f with respect to f, is f2, second component, and third component with respect to z. The application is direct, and it's really very simple. So, by the end of this example, we will be finishing our course. Congratulations for all of you. Now I have z, which is x squared plus y squared minus z less than or equal to 0, and that's an equation of a paraboloid. And the sphere x squared y squared plus z squared less than or equal to 2, and that's within the first octa, which is within the first quartile. X is greater than or equal to 0, y is greater than 0. Yes, we are leaving the z, so we are talking about the first quartile as I told you. The region is x squared plus y squared minus z less than or equal to 0, and x squared plus y squared as I described for you. The vector field for this guy is zx squared cosine squared z, 2xz sine squared z, 2xy cosine y, and it's given, that's the vector field. Using the divergence theory, which means we will need to find the divergence of these components with respect to x, with respect to y, it's going to be 0, and with respect to z for the last component. Okay, let's do it step by step. That's the divergence, definition of divergence. So I'm differentiating with respect to x, the first component, with respect to y, the second component, with respect to z, the third component. So these both two components are going to be zeros, and we will have just only the first component, which is going to be 2zx cosine squared z. That's the gradient vector times the the vector field, which is going to be 2zx cosine squared z. So now this is the divergence part. So that's the divergence part. Instead of dealing with the vector field all over with the surface integration, I will use the divergence, which is as it is. Now, the hack or the main point now is to imagine the boundary. The boundary is a sphere which, it's a paraboloid, and it is intersected with a sphere, and it is in the part of x is greater than or equal to 0 and y is greater than or equal to 0. That's the volume integration that we are dealing with. So once more, let's analyze the boundary. This is the paraboloid that we are talking about, which is x squared plus y squared less than or equal z. This is going to be the shape. And Also, we have the sphere, which is x squared plus y squared plus z squared, let them equal to 2. So that's our sphere, and that's the paraboloid that we are dealing with. And we are shorting our relation to the case of y is greater than or equal to 0, and x is greater than or equal to 0. So we are just only talking about the part that has x and y both greater than or equal to 0s. Here we go. Here we go once more. Thus, just only this part. This is the positive part where x is positive, y is positive, and that's the part that we are dealing with. So once more, here is the shape exactly. That's the boundaries that we need to analyze in 3D. So that's the triple integration. So let's switch to cylindrical coordinates, which is going to be really very simple. Having the polar, and we have z equal to 0. So x is r cosine theta, y r sine theta, and z is equal to z. The dv will be r d theta, which is the Jacobian in the 3 Now I have between the paraboloid z equal r squared and the sphere r squared plus z squared equal to 2. So once you do the relation, you will have the first quadrant, which is from 0 to pi over 2 for respect to theta. On the r, it's going to be r squared up to z equal to 2 minus r squared from direct substitution. So that's the integration that we are dealing with. Of course, the first integration will be with respect to r, so it's going to be really very simple, which is going to lead to r cubed over 3. Then I will go to the theta, to the z direction first, okay, integrating to z, so it's going to be using partial derivatives, as you can see. This is z, okay, this is z cosine squared z, and then we will finish it by the integration in the direction of r and theta, as you can see from the various boundaries about this part. Congratulations, now we finished this session, which covers lectures 19 and 20. So now I can congratulate you about the end of our course for this semester. It contains a lot of information, so please do start to review all of them. I believe we will go for an extra session, inshallah, solving some problems from list number 10. It's really very simple and direct. All we have to do is just to go through it step by step. I believe I will give you another lecture about solving this guy, and then I will do a complete revision about the details of our course from the beginning till the end of our course. Thank you very much for being with us through this journey, and please, I need you to study hard within the coming period in order to be able to solve very good in your exams. Thank you very much. With my best wishes for you all, and thank you. Bye.